So there are particular formulas for surface area of objects that at least have one side or edge that is straight. So for example, the tunnel problem we just did, it had one curved edge, but it had a straight edge as well. And so we were able to use calculus for the curve, but then we could just use multiplication. Okay, there was our tunnel. Okay, if you deal like a Pringles can, you don't even need calculus for the curve. You can use geometry for the curve, and then multiplication for the straight edge. All right, but what we're talking about now is we need calculus for something like maybe a vase or something like this, okay? So both the top and the bottom are curved, but the sides are curved too, and so you need geometry, or you need calculus to be able to do the surface area of all of that. Now last year we did the volume of that, which we'll get to later this week. But right now we want to focus how do you get the surface area of that. It's really not bad. All right, so the definition for surface area. Of course, we're going to need an integral. The integral will go on the bounds. Now, if this thing is upright, like the vase, the bounds will be y terms. If the thing is lying sideways, like a football or something, then the bounds will be x terms. You just have to, your object will be oriented a certain way. All right, so we're going to take the length of the curve, which we just learned, so 1 plus dy dx quantity squared. And then to bring 3 dimensions into this, because we need surface area, we will have 2 pi y.
Is this for any situation?
Dx. Because y is equal to the function, right, in terms of x. We have y and we have dy dx. Right, and then dy. Right. So if it was going the other direction, I guess if you want to say that, if we were going c to d, if we were going right side up, it would be 1 plus dx dy 2 pi x dy. So you've got either x terms or y terms. Yes. Okay. All right, so it is coming back from the geometry formula back in the day. Surface area being 2 pi r times the length. Okay, so Friday, we learned that the length is this, 1 plus the derivative squared. So we've got that part of it. R is the radius of the object you're trying to find. So if we are doing, I'll try and do my vase again. Okay, R will be the length, which is changing all the time. Okay, this is not, because the sides are not straight like a Pringles can. In a Pringles can, the R is always the same. In a vase, based on the axis that comes right down the center, your R, wow, that was a really bad axis. Okay, your R's are always going to change length. The L is the edge out here. That's the L. Okay. If we did, say, a football or something that was, and we're trying to find the surface area of that, your L is the outside edge of that, or an egg, maybe. Okay. But then the R, and your axis will be here. And again, your R's are always changing. They get bigger and then they get smaller again. Okay. r is the value of the function that you're working under. Okay, just like, so if we're doing it this way, these are all y heights. So y1, y2, y3, y4, y5, y6, they're all different y heights. If you're doing a vertical function, these are all different x values. Okay, x1, x2, x3, x4, they're all different x lengths.
Shouldn't it be changed in that radius as well, or we're just finding one instant part?
Yeah, the radius is not constant. That's why the radius is not going to be a letter. It's not going to be a value. It's going to be a function. Okay, if you would rather, if you don't like y right there, if you'd rather have it, y is the same as f of x. If you would rather put f of x right there, those are the same thing. Okay, it is changing. That radius is always changing depending on what f of x is. Okay, if you don't like x right here, you can make that be f of y. Those are the same thing. Okay, it's always changing. So it's the length formula times 2 pi. It's like the circumference. Okay, 2 pi r. Yeah.
You're assuming the volume to be like spherical, kind of like symmetrical?
Yes, these have cross sections that are circular. Yeah, we'll get to cross sections that are triangular or diamond shapes, or that's lesson E3A that is coming. Yes, these all have circular cross sections. All right, so let's try an example. All right, so find the surface area for an object with the x-axis as its axis of symmetry. So the x-axis goes to the center. Circular cross sections. And edge of f of x equals 3x minus x squared. And we'll do it on 0 to 3. Okay, to understand what this looks like, the x-axis is going through the center of this object. Its edge is being formed by an upside-down parabola. The upside-down parabola looks like this, crossing at 0 and 3. And because it has circular cross sections, that means that this thing is reflected over the x-axis. And it's kind of like an egg with pointy ends, or actually it's really shaped nicely like a Vidalia onion. Okay, all right, so yeah, that actually onion's not a bad analogy, because all of these, if you know, an onion is made up of all these circular pieces, right? Okay, this is an onion turned sideways. So we want to find the surface area of this. So just using the formula, it'll be 0 to 3 are my bounds. 2 pi, I'll do my square root at the end. 2 pi f of x times the square root of 1 plus f prime of x squared dx. There's your formula. 2 pi r L. 2 pi radius, length. That is the order how it's going to go. And then you just crank out the antiderivative from there. All right, so we've got 0, 3, 2 pi. F of x is 3x minus x squared. And then the square root of 1 plus the derivative of that. And the derivative is 3 minus 2x quantity squared dx. Let's pull 2 pi out to the front. It's a constant. So we've got the quantity 3x minus x squared on the outside, and the square root of 1 plus 9 minus 12x plus 4x squared. I just FOILed out the derivative. In other words, when I clean that up, let's do 4x squared minus 12x plus 10 dx. So there's your simplified integral. 2 pi is a constant pulled out to the front. Your bounds are set up. The length of the radius. The length of the radius is being formed by the height that's following the curve, and then the square root. And then you can let your calculator do the FNN rest for you once you have your integral set up. Type that into your calculator, and away you go. Yes, sir.
So when you show that from here, we FOIL out everything.
You don't have to. You could have just typed it in, probably. Yeah, right here. You probably just could have typed it in right there. Okay. If you would have your calculator probably for something like this. Sometimes it'll come out where a U substitution would work really well in integrating this. Like the thing under the square root would work out to be a nice U for the thing on the outside. And you wouldn't have your calculator probably to evaluate that, but most of the time you will. Let's try one with an axis that's y. Okay, so the same thing, surface area with a vertical axis of symmetry along the y-axis. So as soon as you know it's vertical, you know you're going to be in terms of y. Circular cross sections. And edge formed by f of y equals 1/3 y cubed. And the bounds are going to just go from 0 to 1. Okay, now, if you have trouble visualizing, if you have trouble visualizing what 1/3 y cubed looks like, think about what 1/3 x cubed looks like. Okay, 1/3 x cubed is going to be a cubic graph that does this. That's 1/3 x cubed. So if you want to draw 1/3 y cubed, it would be the inverse shape of that. And so 1/3 y cubed is going to look like that. Okay, it goes in an inverse, a diagonal reflection of the yellow. So if you have trouble visualizing it, I usually graph it in terms of x so that I can picture it. And then I switch it. That helps me. Okay, so now I've got my graph, and I'm only going from 0 to 1. So I can kind of maybe zoom in on this. And I'm going from 0 to 1 on the y bounds. So that y-axis is the axis of symmetry, and I have circular cross sections. So that means I've got a circle. Ooh, too big. All right, go away. Okay, I've got a circle It's almost like a funnel shape. Okay, so I've got this funnel-shaped thing because the y-axis is down the center, the circular cross-section, so all of these are circles getting smaller and smaller as they go down the y-axis, like a tornado, all getting small. But we just want the surface area of this. And so we can set that up. Our bounds are 0 to 1, 2 pi times the function, which is 1/3 y cubed, and then the square root of the derivative of 1 plus the derivative. So the derivative of 1/3 y cubed is y squared dy. So Bobby, this would actually be something that would work out with a nice u substitution. If I pull the constants out, if I take 2 pi and the 1/3 out, I'll be left with y cubed on the outside, and I'll be left with 1 plus y to the 4th on the inside. This is something we could do by hand, because these the expression that I get under the square root is a nice, really nice u substitution. I can set u to be 1 plus y to the 4th, which means du is 4 y to the 3rd dy. So dy is du over 4y cubed, and my bounds would change also. So this is actually one that would work out really well for us. My constant out front is 2/3 pi. My new bounds are now 1 to 2. I have y cubed. I have the square root of u, and then I have du over 4y cubed. So I can simplify the y cubes, bless you, reducing each other, and I can pull the 4th out. So I'll have 1/6 pi on bounds 1 to 2 of the square root of u du. So it's a very manageable integral. This would be something that would be reasonable for you to do without a graphing calculator. So 1/6 of pi on the outside. My antiderivative will be u to the 3/2 times 2/3 plus c, going on bounds of 1 to 2. And once I've committed to those bounds, I don't need to change them back. I would just stick with 1 to 2. So let's see, 2/3 times 1/6 is 1/9 of pi times 2 to the 3/2 minus 1 to the 3/2. So 1/9 of pi times the square root of 8 minus 1. Okay, any other questions about that one? You could write square root of 8 as 2 rad 2 maybe. Maybe that would be a little better. We'll do 2 rad 2.